and the problem states that Petit loves lucky numbers. Everybody knows that positive integers are lucky if their decimal representation doesn't contain digits other than 4 and 7. For example, numbers 4, 7, 7, 4, 4, 4 are lucky, and 5, 17, 4, 6, 7 are not. Lucky number is super lucky if its decimal representation contains equal amounts of digits 4s and 7s. For example, numbers 4, 7, 7, 7, 4, 4, 4, 7, 4, 4, 7, 7 are super lucky, and 4, 7, 4, 4, 4, 6, 7 are not. One day, Patia came across a positive integer n. Help him to find the least super lucky number, which is not less than n. And the input that we have is a positive integer n that we build across to, and we output the least super lucky number that is more than or equal to n. So for the examples here, we have 4500. Then we output 4747, and note that we can't output 4477 because although it's super lucky and it's the least super lucky, we also need to make sure that the output is greater than the input, greater than or equal to the input. So for this example, we have 47, and we would output 47 again because 47 is already a super lucky number. So for this example, we can use a brute force approach. And what I mean by that is we can try all possible combinations of 4s and 7s and see which one fit within our criteria. So we can use DFS, depth first search, to generate all super lucky numbers up to a certain length. And this certain length would either be n or n plus 2. Why n plus 2? It's because, let's say we have n is equal to 9999, right? Then our output will have to be 4, 7, 4, 7, 4, 7, 4, 7. As you can see, we added 2 extra digits, 1 digit of 4 and 1 digit of 7 at the end. And this is because, it should be 4, 7, 4, 7, 4, 7. I had an extra digit there. But same principle. We have 4, 7, 4, 7, 4, 7. We added 2 extra digits of at the end because there is no possible way for us to be within the same length as n and output a super lucky number that is greater than it. So therefore, we also need to check that the length of the current candidate is greater than or equal to the length of n plus 2. So using a DFS approach, using recursion, we can have something like this, a DFS search tree, right? So if we have a DFS decision tree as well. So if we start off with an empty string as our root node, then for each decision we have 2 choices. We can either add a 4 or we can either add a 7, right? So here we can add a 4, add a 7, and then within those subtrees we can do the same thing over and over again until we meet a valid candidate. And this valid candidate would have to be the integer value of this candidate will have to be greater than n, and we have a equal amount of 4s and 7s. So here is the code, and we initialize a result array, and we take the input as a string right so far. And this is the meat of the logic right here. We have a search function. We take in the current string, we also account for the number of 4s and 7s that we have used. And if the current string is greater than 0 and we have the same amount of 4s and 7s, then we can move on to the next checker. This next checker basically says, okay, if we have a an equal number of 4s and 7s, we then have to check if it's super lucky, right? So the length of the current string has to be greater than or equal to the length of n, and the integer value of the current string is greater than or equal to the int of n. And if so, this passes the super lucky test of the problem, and we can just append that to the result array. And this is the second base case. If the length of the current string is greater than or equal to the length of n plus 2, we just return. This is basically saying we cannot exceed the n plus 2 as the n plus 2 criteria, where this comes back to this example. If we have this, we cannot add this, right? We have to be within the constraints of this length. And then we basically emulate the decision tree, right? So we can either add a 4 or we can either add a 7. And when we do those respective searches, we have to increment the number of 4s and 7s that we have so far. And in order to start this search and append every possible solution to the result array, we just start with the search empty string 0 0, and like I said, since it's a brute force approach, we have every possible values that is super lucky and greater than n, right? So, but we want the least super lucky. So at the end, we just output the minimum of those values within the array that we have built. So in the end, what we did was we used DFS to build all candidates of 4s and 7s, and we explored each branch before backtracking. In that process, the code filters for the super lucky candidates using the conditions of whether it's greater than or whether it's greater than or equal to the length of n plus 2, or we just check if it's super lucky, right, with the two conditions that we have stated here.